Hello, in this video we're looking at volumes. More specifically, we're seeing how we can find the volume of a solid object using integration techniques. There we go. So here's a quick summary. Like we said, we're going to explore how integration can be used to describe volumes of solid objects. The idea is similar to what we did for areas. So for the area, remember the idea was, you can imagine I've got some curve here, and let's say we're going from A to B. And we summed length, so we were kind of adding up these little lengths, in some sense, along a length. And that was the result of a limiting process. So really, we set it up with an approximation using rectangles. But we're thinking of it as kind of adding length across a length. So length by length gives us area. Well, what we're doing now, do that. The idea now is that I've got some solid, any sort of region it might be. It could be real weird, and that's okay. We're adding up cross-sectional areas across a length. So we're adding up areas across a length. So area by a length gives me the volume there. Okay, so the way we looked at it with calculating area, we started with an approximation, and we used rectangles. Now to find volume, we're going to use cylinders. So the idea is the approximating cylinders, well, they're going to be constructed using delta x for the height, and the cross-sectional area would be a sub I. So this would be having to do kind of comparable to, we take a sample point and figure out a function value at that sample point. Now we're going to take a sample point in the interval and figure out the corresponding cross-sectional area. So the resulting cylinder volume is given by that. So kind of a similar setup to what we had for the area approximation, where it was height by a width. Now it's area by a length or width or whatever, however you want to call it. So adding up all those approximations gives you an approximating volume, and when things are nice, as you increase the number of approximating rectangles approximating cylinders, you get a better and better result, and that limiting process will give you the exact value. So trying to pick some colors here. How does this look? Yeah, I think white's not going to work, so how about purple? So if I were to do, maybe some subintervals looking like this, I'd have a cylinder there, cylinder there, cylinder there, and so on. And you can imagine these purple cylinders filled in the space that they enclose. Add all those up, you get an approximation for this solid object. And like I said, you can imagine if we did more intervals, is provided that I've got a nice shape here. I fill it in better and better. Alright, so it's kind of a sloppy drawing, and if you just look at the sketch, it's maybe not going to make a lot of sense, but if you followed along, maybe it made more sense. And you could just imagine if we're doing really, really skinny, really skinny cylinders, where our delta x is going to be this is our delta x, this is our delta x, and so on. So when that's really skinny, I get more and more of them. And as that shrinks to 0, which is equivalent to the number of subintervals, goes off to infinity. If I've got a nice surface here, a nice description, it's going to fill it in better and better and better, and you get the exact area. So kind of a clumsy, lengthy description there, but hopefully that kind of makes sense. So a little bit more formally, here's what we have. Excuse me. So I've got a solid, and we're going to say that it lies between x equals a and x equals b. So imagine you've got that's some sort of weird solid here, S. And I'm going to say it lies between A and B. And if the cross-sectional area of S at the plane X, so any particular X value, say xi star, that cross-sectional area, whatever weird shape it looks like, that would be the area of that cross-section. Well, if we've got these little subintervals, and each one of those is delta x, then this has a little bit of width to it, and you add up all those cylinders and you get your approximation. That would be, looking at it, that would be this part, that's your Riemann sum approximation, and then you let n go to infinity, and if a is continuous, then you get the exact value here as the definite integral. So we kind of imagine that we've got this, if we want to integrate with respect to x, kind of orient our solid in that certain way. All the hard work comes in finding a description for a. That's the tough part of this problem, is finding that function. So in some cases we have a really nice situation. Well, in plenty of cases I'm sure we do, but the one I have in mind is what we call a solid of revolution. So this is a solid obtained by rotating a region about an axis, and that means it has rotational symmetry. In this case, the hard part of these problems are just finding a description of the cross-sectional area. In these cases, that is a much more manageable task. So if the region that you have in question is flush with the axis of rotation, your cross-sections are going to be disks. I'm going to show you in just a second what this looks like. The disk will have area, well, it's a disk, so it's a filled-in circle, so its area is pi r squared. In this case, we say pi of rx squared, where rx is the distance between the curve and the axis of rotation. It serves like a radius. So here's what it looks like. Imagine that, let me get this going a little bit further. Imagine that we rotate, somehow you could pull this into 3 space and twist with your fingers along this axis right here. And this guy starts swinging around, so it goes around this way, comes back up, looks like this. In fact, here it is right here. That's what it would look like. So the idea is, I've got this curve. The idea is, if this solid, which is obtained, this solid right here, is obtained by rotating this region about the x-axis. So it's this region here. Now when I look at something like, let's say right here, this height, what that looks like here is right there in that solid. But when I rotate that around, that piece rotated around sweeps out a region that is a circular region, filled in circle, which is a disk. So this area equals pi r squared, where r is the function value. So that's what I'm saying back here. It's r of x. So that's what it looks like. Now the other situation we have is if you've got, so what I'm saying here is we're rotating about this axis, so it's flush, it's all the way up against it. Now if we rotate about an axis and there's space in between the cross section, it's going to be a washer. It's basically a disk with an inner disk missing from it. So the idea is the shape looks something like this, where I'm limited with how well I can draw it, but that should be the same length all the way around. So out here, this would be capital R. In here, that would be the lowercase r right here. So you take pi capital R squared, that's the whole space, minus pi lowercase r squared, that's the little space, and what's left over with is what you're looking for. It's the area of that washer, not a disk anymore. So there's our area formula, cross-sectional area at a given x. What that looks like here is if I had something like this, I've got this going up to here, bounded below here, and let's say that we rotate this about the x-axis. Then when I've got something like this piece here, it gets swept around and that middle part, that missing part right there, is what's missing in the middle there. So that cross section, probably making it, muddying it up further now, but that cross section is a washer. And it would have area given by this formula. So the area of the whole thing minus the area of the center gives the area of the washer. Alright, so in general, these are tricky problems finding these volumes because you need to find, scroll back, you need to find the cross-sectional area. And that's a tough problem. That's a tough thing to find in general. It's tough to find. It's tough to find a description of that. But again, a lot of our examples, not all of them, but a lot of our examples are going to be solids of revolution. In that case, that A of x is, relatively speaking, easy to find. You either have a disk, which would look like this, or you have a washer, which is a disk with a disk missing from the inside. Looks like that. So those are your two options as solids of revolution. We also want to know the general case as well. And yeah, that's it for this.